Hi everyone, my name is Dami, and it is my pleasure to present to you the project I worked on while working as an Insight Data Science Fellow. So I call this project Next Check, which is short for Next Checkup, and it's a consulting project for a dialysis access facility to help predict how long it takes for their patients to return for vascular access surgeries. So to start with, what is vascular access? Vascular access is a surgery, or more or less a procedure performed on dialysis patients to establish connection between their blood vessels and the dialysis machine. So these patients require this because they have lost their kidney function, which means they can no longer on their own filter out their blood for impurities and toxic waste. So they need an external means of doing that, which is a dialysis machine. So the vascular access surgery is considered a lifeline because it establishes a connection to a dialysis machine, and thus they have a lifeline. However, this procedure has or often develop complications, and so sometimes it's referred to both as a lifeline and an Achilles heel. So the scale of the problem is you have about 500,000 patients, dialysis patients in the US, and these patients are burdened by hospital admission costs. So the challenge is trying to find an appointment date for them that is appropriate such that they get clinical examination before those complications arise. So I use the data set on dialysis patients from a particular dialysis access facility to predict how long it takes for those patients to return based on the procedures performed on them. So the goal is to get out a model that helps doctors decide when it's best to schedule checkups so that timely intervention can be performed and their lifeline kind of extended, more or less. So the data set was obtained from Savannah Vascular Access Institute, and it had data for about 2,400 patients. And I also had 400 variables, basically. Out of those 400 variables, I had to remove those that had missing values, entirely missing values, and were like duplicates. So eventually I ended up with the data that had the response variable, which is the time interval between procedures, and predictor variables, about 142 of them, which describes the various procedures the doctors or the vascular surgeon performed relating to whether they did a thrombolysis, which is to fix blood clot, whether the patient had prolonged bleeding, whether it had a swelling of the blood vessels, the kind of vascular access itself performed, which is whether it's a vascular, a fistula, or a graft. So my project workflow was first to wrangle the data, just to clean out the data. So I had to do a log transformation of the response variable because the data was skewed. I did one hot encoding to put each categorical variable, to break each categorical variable into separate classes, like individual columns for each class. And I did simple imputation, which is to replace missing values in my numeric predictor variables with the average means for respective columns. And then I did a random forest model. So I used a grid search to get the optimal parameters, and I did hyperparameter tuning to improve the fit of the model. So I used the model finally to build a web app, which is like a decision support tool for doctors to help get a predicted date for them to schedule next appointment for checkup. So just a brief overview of how I went about exploring the data. So here is a histogram that shows the response variable, which is interval between dialysis access surgeries. So you can see you have some missing values and the data is skewed. So when I did a log transformation, some symmetry was restored to that variable, and it was the log values I used eventually in building the model. So the mean response variable is 179 days, and you have a maximum value of about 1,600 days. So here, looking at how predictor variables might affect the response variable, you can see patients that do not have thrombolysis performed tend to take longer before they require another vascular access surgery compared to those who had thrombolysis performed. Similarly, those who only elected for the surgery tend to take longer to return as against those who had to perform the surgery out of emergency. So looking over at the model, you can see fluoroscopy time here was the most important predictor variable for the model. And as well as we had lidocaine, which is how much of anesthesia was used, and yeah, the age of the patient as well. So I had a mean absolute error of 3 days, contrasted with the average, overall average for the response variable of 179 days. It appears our model is doing fine. So here is a quick checklist to show you how the model would perform or how the web app would work. So if I were to be a doctor, I would impute values for fluoroscopy time, which is say on the average about say 85 minutes. How much of anesthesia I use, say 5 cubic centimeters. The age of the patient, let me impute the average age of all the patients in the data set, which is 65 years. Whether I did a clot access and whether the patient had issues with the artery. So let's assume the patient had none. I could submit this impute data and get an output, which gives me an estimated number of days the patient might return and what that date is from the current date. So in this case, it's 74 days from today, and which is 25th of April, 2020. So basically that is how the app would work. And in conclusion, I would like to say that doctors need an evidence-based determination of appointment dates. And it is crucial, this is crucial to preserve the dialysis access as a lifeline. So my web app works as a decision support tool to help achieve this objective. And the web app can be integrated into the existing patient record database. So overall, this would improve health outcomes, lower cost because the patient gets care before they require very serious surgeries, which are much more expensive and longer hospital stays. So you have improved health outcomes and lower healthcare costs as a result of this app. And then a brief overview of myself and my background. So my primary training is in plant biology. I've been attending institutions across 3 continents, in Africa, in Europe, and in the US, where I'm finishing my PhD. And I have certifications in accounting and finance. I'm an affiliate chartered accountant of the UK. And I have work experience in banking, audits, and at present, I'm a fellow with Insight Data Science. And I hope I can bring my wealth of knowledge and experience to help this organization achieve our objectives. Thank you.